Hello everyone, welcome again to EGN 3343 Thermodynamics, and we are going to continue with our applications of the second law of thermodynamics, and this time around we are going to apply it to those problems involving ideal gases. And remember that ideal gases are basically pure substances that operate far away to the right of the saturation dome, and a region in which the saturation dome doesn't exist. It's too small and too far away to the left. So basically, we are operating at pressures and temperatures far away from the ones that are going to make this gas change phase. We basically call air, hydrogen, oxygen, CO, CO2, and nitrogen ideal gases. It doesn't mean that these gases cannot, under certain conditions, change phase. We know that liquid oxygen and liquid nitrogen exist and liquid hydrogen exist for certain purposes, but they would have to actually be taken to extreme conditions, extreme values of pressure, very, very high pressure and very, very low temperatures in order for them to become liquid. Under standard conditions and regular operating conditions, these gases only operate on the in vapor form, and they respond to a state equation. And their properties, their fundamental properties, pressure, volume, and temperature, are related very nicely algebraically through a state equation. Now recall that for ideal gases, the state equation is maintained. Pressure times specific volume is equal to the gas constant R times the temperature. Recall also that the change in energy is equal to the specific heat at constant volume times the change in temperature, and the change in enthalpy is equal to the specific heat at constant pressure times the change in temperature. This is in differential form, and it can also be done in finite form. So if you want to calculate the change, not the differential of energy, but the change of energy, you would have to integrate this. So that yields two models. A model in which the specific heats can be considered to be constant, in which case it will come out of the integral, and you can basically say that the change in energy is equal to CV times the change in temperature, and the change in enthalpy is equal to Cp times the change in temperature. Or there are models where Cv and Cp cannot be considered to be constant, and then you use a table. You need a table that is essentially organized only by temperature, because in ideal gases, energy and enthalpy only depend on temperature. So the table for ideal gases are basically organized only in temperature. And that's only necessary when you cannot assume the specific heats to be constant or average. Now we're going to go back to these TDS equations that we defined and that we formulated a couple of lectures ago. And the TDS equations were some differential equations that expressed the changes in entropy as a function of the changes in energy and the changes in volume. The first TDS equation said that temperature times the change in entropy is equal to the change in energy plus pressure times the change in volume. And what we're going to do is that, because we're talking about ideal gases, we're going to replace du by Cv dt. And then we're going to divide the left and right hand side of this equation by the temperature. So on the left hand side, we're going to end up with only entropy. So the change in entropy is equal to Cv dt over T. Cv times the change in temperature divided by temperature, plus pressure times the change in volume divided by temperature. And then on this right hand side, we're going to use the state equation. Remember that a state equation says that pressure times volume equals R times temperature. So pressure divided by temperature is equal to R divided by volume, directly out of the state equation. So pressure divided by temperature is equal to R divided by volume. So now we have an equation that says that the change in entropy is equal to Cv times the change in temperature over temperature, plus R times the change in volume over volume. That looks like something that we can directly integrate. So if we want to calculate the change in entropy from state 1 to state 2, we know now that we can get an equation that is a function of the change in temperature and a function of the change in volume. So now we know that the entropy change for an ideal gas is a function of the temperature and a function of the volume. How is that? Well, before we do that, let's look at the second TDS equation. This is a result of the first TDS equation. This is a resulting differential equation that is solvable for the first TDS equation. And for the second TDS equation, remember we had TdS is equal to dH minus VdP. Temperature times the change in entropy is equal to the change in enthalpy minus volume times the change in pressure. Let's use the relations for ideal gases, where dH is equal to Cp dt. And let's divide everything by temperature. So now the change in entropy is equal to Cp times dt over T minus V over T times the change in pressure. Now we're going to use the equation of state, and remember that P times V is equal to RT. Therefore, V divided by T is equal to R divided by P. Directly out of the state equation that applies to all ideal gases, where R is the gas constant. One for air, one for CO2, one for hydrogen, and so on. So now this leads to an equation where the change in entropy can be easily calculated as Cp times the change in temperature over temperature minus R times the change in pressure over pressure. So now we have two equations for entropy. One that calculates the change of entropy as a function of temperature and volume, and the other one that calculates the change in entropy as a function of temperature and pressure, depending on what we have. If we have the temperature and pressure of state 1 and state 2, we can calculate the change of entropy. If we have the temperature and volume of state 1 and state 2, then we can calculate the change of entropy using the other equation. Alright? But now, these are not yet algebraic equations. These are so-called differential equations. We need to solve that equation. So, these are the two equations we have. Change in entropy as a function of temperature and volume. Change in entropy as a function of temperature and pressure. To determine the entropy change for a finite change in state, from state 1 to state 2, not differential change, not infinitesimal change. These are equations, differential equations, for a little piece of state, a little differential state, an infinitesimal change in state. We want to determine the change in entropy from state 1 all the way to state 2. And what we do is integrate this whole thing. Okay? So we say that the change in entropy, not ds, but delta S from 1 to 2 is the integral of these plus the integral of these. Now, this will depend on whether we can assume that the specific heats are constant or variable. Okay? Because now remember that delta S is going to be the integral of these plus the integral of these. Now we know that we can take R out of the integral. It's no big deal because R is a constant. We know that. But CV is not necessarily a constant. We might have to leave it inside the integral. But under the constant specific heat model, CV may be assumed to be a constant and we can take it out of the integral. So the change in entropy from state 1 to state 2 becomes now the change CV times, assuming that CV is a constant, we took it out of the integral, times the integral from T1 to T2 of dt over T, plus R, we took it out of the integral because R is a constant, we don't have to assume anything, the integral of V1 over V2 of dV over V. Now we know that the integral of dt over T is the log of T, and we know that the integral of dV over V is the log of V. When evaluated between T1 and T2, that's the log of T2 over T1, and when evaluated between V1 and V2 is the log of V2 over V1. And there it is. The change in entropy between state 1 and state 2 according to the TdS equations for ideal gases using the constant specific heat model is CV times the log of T2 over T1 plus R times the log of V2 over V1. So knowing the temperature and the volumes at state 1 and state 2, we can calculate the entropy. We don't need tables. Okay? All we need is a simple equation. Same it goes for the other TdS equation, which after integration and taking Cp out of the integral because we're assuming constant specific heats, the change in entropy from state 1 to state 2 becomes Cp times the log of T2 over T1 minus R, the log of P2 over P1. Okay? So now, if we knew the temperature and the pressure in one state and the temperature and the pressure in the other state, we can use that to calculate how much the entropy changed between those two states. Furthermore, how about when the process is isentropic? How about when a process is adiabatic and reversible? We know that when the process is adiabatic, no Q, and also reversible, there is no change in entropy. So if there is no change in entropy, what I'm going to do is I'm going to take the first TdS equation, the one that says Cv log of T2 over T1 plus R log of V2 over V1, and I'm going to make it 0, because I am saying, well, what happens when the entropy doesn't change? How do I relate temperature and volume, for example, in processes where the entropy doesn't change? Well, there it is. I'm going to make this 0. Then I'm going to take this to the right-hand side. minus r log of v2 over v1. Then I am going to take this minus sign, and by properties of the logarithms, I am going to switch v2 over v1 to v1 over v2. That's what the minus sign does in front of the logarithm. And I'm going to take the r, I'm going to take the cv and send it as a denominator of r, and then I'm going to take that factor as an exponent of the argument of the logarithm. That's just properties of logarithms. Now, because the log of these is equal to the log of these, then this one has to be equal to this one. I can just solve for t2 over t1 by taking the e to the power of these and e to the power of these. Also properties of the logarithms. By the way, you don't have to remember how to do this. I'm just deriving the equation for you. At the end of the day, this equation is readily available. So what we have is t2 over t1 equals to v1 over v2 to the power of r divided by cv. Now, r is the gas constant, and is defined as the subtraction of Cp minus Cv. It's the difference between specific heat at constant pressure and specific heat at constant volume, Cp minus Cv, by definition. And there's another constant, K, that is defined as the ratio of specific heats. It's called K, or the isentropic constant. For a reason, it's called the isentropic constant, or the ratio of specific heats. You can find it in tables where you find Cp and Cv. For air, there's a table for Cp and Cv at different temperatures. The difference between the two is the R, and the ratio of the two is K. So we are going to replace R by Cp minus Cv, and then that will be Cp over Cv minus 1, and Cp over Cv is K. So the ratio of R over Cv can be replaced by K minus 1. Furthermore, I'm going to take all the state number 1 to the left hand side. So I'm basically going to take T1 multiplying on the left, on the right, and V2 multiplying on the left, knowing that it has an exponent. And that leads to this equation. This is an equation that relates temperature and volume of two states that are separated by an isentropic process. So if the process from 1 to 2 is an isentropic process, if we are told that the process from 1 to 2 is a process in which the entropy doesn't change, or it's an adiabatic and reversible process, this is how we relate the temperature and volume. So let's say that we have temperature 1 and volume 1, and we also have volume 2, and we know what gas it is, so we know K. That means that we can solve for T2, or any other quantities. If we have 3 of these quantities, we can solve for the other one. If we have the initial temperature and the 2 volumes, we can solve for the final volume, as long as the process is isentropic, and as long as we can assume that the specific heats are constant. Okay. Furthermore, we can take that same equation, T1v1 to the power of k minus 1 is equal to T2v2 to the power of k minus 1, or any two processes that are isentropic. I'm talking about process 1 to 2, but it can be process 3 to 4. Okay. And I'm going to use a state equation again. I'm going to say that P times V is equal to RT. So I'm going to replace temperature 1 by PV over R1, and I'm going to replace temperature 2 by PV over R2. This R and this R will go away. This will be P1 times V1 to the K minus 1. And notice that V1 times V1 to the K minus 1, the minus 1 will go away with the 1 on this V1, and the minus 1 will go away with the exponent or the power of 1 on this V2. So at the end of the day, we get P1 V1 to the power of K is equal to P2 V2 to the power of K. That's what that equation comes from. This is the equation of an isentropic process that we derived many lectures ago. This is exactly where it comes from. P1 V1 to the K is equal to P2 V2 to the K. By the way, this is the same equation as this one. There's no difference. It's just this one just relates pressure and volume, and this one relates temperature and volume. But it will yield the same results. This is for the case where you have, let's say, pressure 1 and pressure 2 and one of the volumes, then you can determine the other volume. Or if you had the 2 volumes and have one of the pressures, then you can determine the other pressure. Well, likewise, you can use the equation of state to replace V1 in this equation for RT over P. RT over P. You replace that, and that will yield T1 P1 to the power of 1 minus K over K is equal to T2 P2 to the power of 1 minus K over K. This is the same equation, but now expressed in terms of T and P, rather than T and V or P and V. So now you have 3 equations that are exactly the same for an isentropic process relating two properties at two different states. By the way, this is the table A20, which is posted on this wall for you. This is the equation where you can find Cp and Cv at different temperatures, and you can find K. The ratio of the two, notice, it doesn't remain constant. So it's very important that if you use a constant specific heat model, you use it at the right temperature. If the process takes place somewhere between 500 and 700 Kelvin, make sure that you take an average. The average in the temperature in this process is about 600 Kelvin. That means that Cp is 1.05, Cv is 0.764, and the ratio of the two is 1.376, if we're talking about air. You can do that for any of the other quantities. Finally, this is how this curve, P times V to the power of n equals to a constant, with the so-called polytropic processes, would look in a PV diagram or in a TS diagram. Remember that the polytropic process can be specified depending on the value of n. If n is equal to 1, we're talking about an isothermal process, because PV, which is equal to RT, then if RT is constant, then this is an isothermal process. If n is equal to K, the ratio of specific heats, it's no longer a polytropic process, but an isentropic process. Now let's talk about n equal 1, isothermal. PV equals to a constant. We know that in the PV diagram it would look like an asymptote. And in the TS diagram, it would look like a horizontal line. Temperature is in the y-axis, so it would not change, so it would be completely horizontal. For n equals 0, an isobaric process, if n is equal to 0, then P is equal to a constant. In a PV diagram, it will be a perfectly horizontal line. In a TS diagram, it will be a growing exponential. This is an n equals 0, or P equals to a constant line. This is an isobaric line in a TS diagram. When n is equal to K, K being the ratio of specific heat, this is an isentropic process. Then P times V to the K is equal to a constant. Remember that K is always greater than 1, because K is Cp over Cv. Cp is always greater than Cv because the difference between Cp and Cv is R. In the PV diagram, that would be an asymptotic line with a little steeper slope than the isothermal line. In the case of the TS diagram, it will be a perfectly vertical line. When entropy doesn't change, the process is indicated by a vertical line in the TS diagram. And when n is equal to infinity, we're talking about an isometric process, a process where volume doesn't change. And if volume doesn't change, we have a vertical line in the PV diagram. Obviously, volume is in the x-axis, so it's a vertical line, n equals to infinity. And then the TS diagram is a growing exponential with a little bit steeper slope than the isothermal line, or the isobaric line, I'm sorry. So there it is. These are how you remember, we're talking about ideal gases, so there's no saturation dome, neither in the pressure volume diagram, PV diagram, or in the TS diagram. So these are different process lines for the different types of processes in these two diagrams. Alright, now let's go directly into the implementation of these concepts of finding the entropy changes in ideal gases. And let's solve a problem where we have air, which can be considered an ideal gas, and we're given the value of Cp, so we don't have to look it up in the table. It's 0.241 BTU pound Rankine, so this is in US customary units. It's compressed from a state where the pressure is 15 psi and the temperature is 80 Fahrenheit to a state where the pressure is 50 psi and the temperature is 240 Fahrenheit. We're being asked whether these processes can occur adiabatically. Okay? In order for a process to occur adiabatically, Q equals 0, the change in entropy has to be either 0, in the case of reversibility, or greater than 0, in the case of irreversibilities. If we find that the entropy went down, then this process is impossible for these processes to occur adiabatically. If yes, determine the work. If no, determine the direction of the heat transfer. Sketch the process line in a TS diagram. So we have air, that's an ideal gas, that is being compressed from 50 psi and 80 Fahrenheit, which is 540 Rankine, to 50 psi and 240 Fahrenheit, which is 700 Rankine. Okay? What conditions must be true for this process to occur adiabatically? Well, the condition is very simple, that delta S is greater or equal than 0. If delta S happens to be 0, then Q cannot be equal to 0. So let's calculate delta S using the equations that we know. Well, since we have temperature and pressure, let's use the temperature and pressure equation for delta S. And let's not use the temperature and volume, although we could use the temperature and volume equation if we calculate volume at state 2 and volume at state 1 using the state equation. But we don't have to do so. So, delta S is Cp times the log of T2 over T1 minus R, natural log of P2 over P1. Cp is given at 0.241 BTU pound Rankine. Temperature 2 over temperature 1, the natural log of that. Remember that you must use absolute scales. 700 Rankine divided by 540 Rankine. Never use Fahrenheits. Minus R, the universal gas constant and US customary units is 1.98 BTU pound mole over Rankine, and the specific or the molecular weight of air is 28.97 pound divided by pound mole. That would get rid of the pound mole and will give you the gas constant for air. And that multiplies the log of 50 over 15 psi. The change in entropy is calculated to be negative 0.0197. That means that in order for this process to occur, there has to be a heat rejection. There's no way for a process to yield a negative change in entropy or a decrease in entropy if there wasn't a change or a rejection of heat. Heat must have been released from this. Since delta S is negative, the process cannot occur adiabatically. There must be heat transfer out of the system. So that's the answer. There has to be heat transfer out of the system. How much it is? Well, we don't know. We could calculate the change in energy, for example, because we have the temperatures of the two states. We don't know how to calculate the work because we don't know the shape of the curve. This is the shape of the curve in the TS diagram, or the direction of the curve. We don't know what shape it takes, either in the TS or the PV diagram. We just know that it goes from 1 to 2, and it does so in an entropy reduction manner. The entropy is decreased as we calculated, but that's the only thing we know. All right. So now let's go back to the TDS equations, the ones that we integrated to find this relationship for entropy. And now let's assume that we cannot use the constant specific heat model. We cannot take the CP's out of the integral. We know that the change in entropy from 1 to 2 is the integral of Cp dt over T according to the second TDS equation minus R, the integral of dP over P. Now the R we could take out of the integral because R is a constant, no questions about it. And Cp now cannot be taken out of the integral because we're talking about the variable specific heat model. Now, we cannot take it out of the integral, but we know for a fact that this integral right here is only a function of temperature. Because Cp, for an ideal gas, is only a function of temperature. It only changes with temperature. We know that. We're given a table as a function of temperature, and we know that Cp only changes as a function of temperature. And dt over T is just temperature. It is the differential temperature over temperature. Now, this integral could be solved if we had an algebraic form for Cp, if we knew that Cp is a polynomial of the temperature, and sometimes it can be approximated as such. Cp is a third order polynomial of the temperature, for example. But in general, we just tabulate those values. And what we're going to do is we're going to separate this integral. We're going to call this integral S0. S0 is not the entropy, it's just a component of the entropy that is given by this little integral here. It is a component of the entropy. So the resulting values of this integral are called S0. It's S0 at temperature 2 is called S02, and S0 at temperature 1 is called S01. Since this is only a value of temperature, we can go to the temperature tables for ideal gases and then subtract those values or extract those values from those tables at the corresponding temperatures. S0 is only a function of temperature. either a temperature 2 or a temperature 1. And then the second one we can just solve because it's the integral of dP over P, which is the log of P2 over P1 times R. S0 is a function of temperature found on ideal gas tables. Let's go to a table right away. These are the tables of ideal gas, for example, for air. Notice that it's only a function of temperature. It is not like the tables for pure substances where you have to go with temperature and pressure, or temperature is some of the things to extract the rest. In this case, you go in with temperature and subtract the enthalpy, the energy, and now this value called S0. Remember, S0 is not the entropy, it is a component of the entropy. So you have to complete the equation. As entropy change from 1 to 2 is the S0 change minus R, the log of P2 over P1. Alright? And because we're using the variable specific heat model, we cannot say that, for example, delta H is equal to Cp times delta T. We have to calculate H2 and we have to calculate H1 at the corresponding temperatures. We cannot take that Cp out of the integral or that Cv out of the integral. Furthermore, this is the equation we have. Delta S from 1 to 2 is equal to this entropy component called S0. It's not entropy, it's just an entropy component. It's the component of the entropy that is only a function of temperature. And this is the component of the change of entropy that is only a function of the pressure. Okay, so we go to the table. We go to the table and extract that. Now furthermore, what happens in isentropic processes? Using the constant specific heat model, we found that we took that equation of delta S equal to 0 and we manipulated it algebraically and found that P times V to the K is equal to P times V to the K from state 1 to state 2. Now we cannot do that in this particular case. We cannot do that because we don't have an equation to relate temperature and pressure directly. We have an equation that relates S0 to pressure. For isentropic processes, we make this delta S equal 0. And now what we have is that the log of P2 over P1 is equal to S02 minus S01 divided by R. We're just solving for these. So now let's solve for P2 over P1, and that is the exponential of S02 divided by R divided by the exponential of S01 divided by R. Now this expression here, the exponential e to the power of S02 divided by R, we're going to call PR. PR is equal to the exponential of S0 divided by R. And that PR can be found in the table. And now we know that for isentropic processes, this relationship is maintained. P2 over P1 is equal to PR2 over PR1. Where PR doesn't mean relative pressure, it means reversible pressure. Is a value that is related to temperature, not to pressure, that works for variable specific heat model. So now we can relate pressure state 2 and pressure state 1 to the temperature state 2 and the temperature state 1. That's how we relate pressure and temperature in two states. PR is a function of temperature because it's a function of S0. It's E to the power of S0 divided by R. Likewise, we can do the same with the volumes. If we say that P2 over P1 is equal to PR2 over PR1, remember, only for isentropic processes. This equation is only valid for isentropic processes. When 1 to 2, there's no change in entropy. Now let's use PV is equal to RT, the state equation. So let's replace P2 by RT2 divided by V2, and let's replace P1 by RT1 divided by V1. And now let's flip this, and we have V2 over V1, cancel the R's, is equal to T2 over PR2 is over T1 over PR1. Now remember that PR was a function of temperature. It was E to the power of S0 divided by R. And therefore T divided by PR is also only a function of temperature, so we can include it in that table. Let's call it VR. VR is equal to the temperature divided by PR. So V2 over V1 is equal to VR2 over VR1. Only for isentropic processes when using the variable specific heat model, using tables. Let's go to that table again and notice. Again, we go in with the temperature and subtract H, which is only a function of temperature, U, which is only a function of temperature, S0, not the entropy, but that entropy component that is only a function of temperature. We can extract PR and VR, but notice that those are only useful when the change in entropy from one state to another is equal to 0, only for isentropic processes. Remember that PR is just simply e to the power of S0 divided by R. You can do the calculations yourself. You can take S0 divided by R, which is 0.286, and take e to the power of that, and you'll find PR. And you can also do the calculations yourself for VR. VR, remember, is T divided by PR. 250 divided by 0.7329, and so on and so forth. It will yield VR. Okay? Those values can be extracted uniquely as a function of temperature, but they're only useful for isentropic processes. Only for isentropic processes. Okay. Okay, now using these ideas of calculating the change in entropy for processes involving ideal gases, whether using the constant specific heat model or the variable specific heat model, let's solve a problem involving air, which is an ideal gas, undergoing a cycle. So it's a set of processes leading to the initial state and consisting of 3 internally reversible processes. The process 1 to 2 is an isothermal compression from a pressure of 1 bar to a pressure of 4.75 bar. So we go from 1 bar to 4.75 bar at a constant temperature. We don't know what the temperature is. So from state 2 to state 3, we go at constant pressure. So it would be the same pressure of state 2, which is 4.75, to a temperature of 390. So in state 3, we have a pressure of 4.75 and a temperature of 390. So we have 2 things in state number 3. And then we go back to state number 1 through an adiabatic process. And since we are told that this is internally reversible, this is adiabatic and reversible, basically meaning isentropic. So from 3 to 1, we go back in an isentropic process. So, employing the ideal gas model with variable specific heats. Okay, let's not use the constant specific heat model, although you could, and then try to compare the solutions, but I'll leave that as an exercise for you. Let's calculate or sketch the cycle on a PV diagram and a TS diagram. We are to determine whether this is a power cycle or a refrigeration cycle. Remember that in a power cycle, the work net produced is positive, and in a refrigeration cycle, the work produced is negative. It also means that it is clockwise in a PV diagram and in a TS diagram, and in a refrigeration cycle it's counterclockwise in a TS diagram and in a PV diagram. If this is a power cycle, let's determine the thermal efficiency, and if this is a refrigeration cycle, let's determine the coefficient of performance. In either case, there are things to calculate. So here's the summary conditions, and we are going to do this, and we're going to calculate everything there is, regardless of whether we need it or not. What we're given is the pressure of state 1, pressure of state 2, 4.75, and also the pressure of state 3, 4.75. It's the same. And we're given the temperature at state 3. We are told that from 3 to 1 is an adiabatic and reversible process, so the entropy must be the same. Okay, not entropy 0, the entropy. And we're told that from 1 to 2 the temperature is the same, whatever that is. All right, now we are going to fill out this table with volume, entropy, energy, S0, which is not the entropy, remember, is a component of the entropy that's only a function of temperature. PR, which is a function of temperature, and VR, which is also a function of temperature found in those tables. Now, we know that PR and VR are only going to be used, we can find it for any temperature, but we know it's only going to be useful for isentropic process. They only have a meaning in isentropic process, on the process from 3 to 1. Alright, so now let's try to plot these in a PV diagram, where state number 1 is here at a pressure of 1 bar. State number 2 is at a higher pressure, 4.75, and we know that it is an isothermal process. An isothermal process is an asymptotic curve with low slope, about 45 degree slope, obviously. P times V is equal to a constant. From 2 to 3, we have an isobaric process. Now, how do we know it goes to the right? How do we know that 2 to 3 doesn't go to the left? Well, because we know that the process from 3 to 1 is an isentropic process. The process that closes is an isentropic process. And isentropic processes in the PV diagram have a slope that is larger than the slope from 1 to 2, that's the slope of an isothermal process. And because it's larger, it's steeper, 3 has to be to the right of 2. If we had written 3 to the left of 2, then the slope from 3 to 1 will be smaller than the slope of 1 to 2, and that would not be an isentropic process. There it is. It's an adiabatic reversible process, or an isentropic, which could be approximated as P times V to the K equals to a constant, although this equation cannot be used because we are going to use the variable specific heat model. So this equation is not valid. In the TS diagram, well, we know that from 1 to 2, we have a constant temperature process, whatever temperature that is. And we know that is the temperature remains constant, and the volume is going down, as depicted here, and the pressure is going up. So it goes to the left. From 2 to 3, it's an isobaric process. We know isobaric is a positive exponential function in the TS diagram. And it's going to go up to a point 3 that is in line with point 1, because from 3 to 1 we have an isentropic process. This has got to be a vertical line. From 3 to 1, remember, it's an adiabatic reversible process, so it closes that way. So notice that in both of these cases, we go clockwise. So the net amount of work, as you can see in the PV diagram, which is the area under the curve, is positive. That means that this is a power cycle. We can also determine that from the TS diagram. It's clockwise. So the net amount of heat is positive. There's got to be heat in more than what there is heat out, more than heat rejected. And therefore, this is a power cycle. Okay? These are the equations we have. PV equals to RT. It applies because this is an a problem involving an ideal gas. First law of thermos is that Q minus W is equal to delta U. Work is the integral of PdV on each one of these processes. Q is the integral of TdS on each one of these processes, if we can use that for anything. The change of entropy between state 1 and state 2, or state 2 and state 3, or state 3 and state 4 is always equal to S0 at the final state minus S0 at the initial state minus R log of the final state divided by the pressure of the initial state. That is true because we're using the variable specific heat model. We're going to be using tables. Otherwise, we could replace this with Cp times the log of T2 over T1. And the efficiency of the power cycle is the net work of all the processes divided by the heat in. Whenever there is heat in, we have to add it. Whenever there is positive Q, we have to calculate it and add it and include it in the denominator here. Or we can replace we can replace W net by Q in minus Q out, and the efficiency can be given by 1 minus Q out over Q in. It's your choice, whichever one of the two you want to use. They're going to yield identical results. Now let's start with state number 3. Let's go back to the table and notice that in state number 3 we have two things. That means that we can have whatever we want. We can calculate the volume through the state equation. We can calculate H, U, S0, PR, and VR through the table, knowing the temperature. So, using the equation of state, V3 is equal to RT3 divided by P3. R is 0.286, temperature is 390, pressure is 4.75, remember, take that into kilopascals to make this consistent units. 4.75 bar is 475 kilopascals. That yields 0.2348 cubic meters per kilogram. Now we're going to go into the tables at 390 Kelvin. Tables for air, remember they are always organized by temperature, and we extract enthalpy, energy, S0, PR, and VR. And we write that in the table. That's it. So that column of state 3 is completed. You don't need anything else. Now, In the other two states, we only have one thing. That means that we cannot complete the table. We have to relate one of these states to another. Now, we already related state 2 to 3 through the pressure, this constant pressure process, so we cannot do anything else. Our only shot here is to relate state 3 to state 1. And we do that by saying, well, we were told that the process from 3 to 1 is an isentropic process. It's a process where entropy doesn't change. So in the process where entropy doesn't change, remember, we can either use this relationship of P1 over P3 is equal to PR1 over PR3. That only applies to isentropic processes. Or we can use the equation that says delta S is equal to S01 minus S03 divided, or minus R times the log of P1 divided by P3. Make that delta S equal 0 and then solve for S0. We could do that as well. We could potentially solve for S0 directly and then go back to the tables and calculate the rest of the things. So, let's use this methodology. It says, since the process from 3 to 1 is adiabatic and reversible, then delta S is equal to 0. For processes where delta S is equal to 0, we can relate these pressures to the PRs. P3 over P1 is equal to PR3 over PR1. We could also say the opposite. P1 over P3 is equal to PR1 over PR3. Now, we're going to use this because we know that, well, we know P3, we know P1, and we know PR3. So we can solve for PR1. PR1 is equal to PR3 times P1 over P3. So PR1 is 0.7329. What do we do with the PR1? Well, we know that PR is an exclusive function of temperature. So there's a temperature that corresponds to this PR. So we go back to the tables of air. We look in the columns of PR until we find something similar to this value that we found, 0.7329, that we found from the equation. And coincidentally, we found one that's identical. Well, that's a coincidence because normally you'll find something that doesn't match and you have to interpolate in between two values. But luckily, again, PR is equal to 0.7329, and that matches exactly one entry in the table. That means that temperature 1, the temperature that corresponds to that PR, is 250, entropy is 250.05, energy is 178, so on and so forth. So we use those values and plug them in the table. Temperature is 250, entropy 250.05, energy 178.28, entropy 0 is 1.51917, and VR in case we need it, but we don't really need it. We could use it knowing that the ratio of VR1 to VR3 is equal to the ratio of V1 over V3, and we can solve for V1 that way, since the process from 3 to 1 is isentropic. Or we can just use the equation of state and solve for V1 using P and T1. There it is. V1 is RT1 divided by P1. We found that T1 is equal to 250, and V1 then is equal to 0.715. So we stick that in here, 0.715. Also remember, we could have used this ratio of VR because the process from 3 to 1 is an isentropic process, so we could use PRs and VRs. So we know that V1 over V3 is equal to the ratio of VR1 over VR3, which is about 3 to 1, as you can see. So this volume 1 should be about 3 times larger than volume 3. Now we were also told that the temperature in 1 is equal to the temperature in 2. The process from 1 to 2 is isothermal. So what we're going to do is copy this temperature here, and since it's the same temperature, all these quantities are the same. Because remember, H, energy, entropy 0, or S0, not the entropy, but S0, PR and VR, only depend on temperature. So what we're going to do is copy that temperature over, and so we copy the entropy, copy the energy, copy the S0, copy PR, and copy VR. The only thing left to calculate is V2. V2 we can calculate directly using the equation of state. We have pressure and temperature. We can calculate volume. Or very simply, notice if the temperature stays constant, remember that P times V is equal to RT. We can relate state 1 to state 2 and say that P times V of RT in state 1 is equal to P times V times RT in state 2. Since the temperatures are the same, then P times V of state 1 is equal to P times V of state 2. So that means that the pressure of state 2 has to be 4.75 times smaller than the volume. Since the pressure of state 2 is 4.75 times larger than the pressure of state 1, the volume of state 2 is 4.75 times smaller than the volume of state 1. So there it is. Volume 1 is 0.1505. Okay. So here's the summary conditions. 0.1505. This is exactly 4.75 times smaller than this one. Now the entire table is completed. Now we can use it to calculate the values at each of the processes. Let's start from process from 1 to 2. The process from 1 to 2 is an isothermal process. In ideal gases, an isothermal process means the energy change is equal to 0. So Q from 1 to 2 is equal to W from 1 to 2. That way we can calculate the heat, and we can if we calculate one, we have the other. Let's calculate the work. We know that the process is isothermal. Okay, work is equal to the integral of PdV. We did this already. For isothermal processes, the work is RT times the log of V2 over V1. That can be easily done by replacing pressure with the equation of state. It's RT over V. Remember, since T is a constant from state 1 to state 2, we can take it out of the integral. So we can with R. So RT1 come out of the integral, and it's the integral of dV over V. This is the log of V2 over V1. So there it is. Work from 1 to 2 is gas constant times temperature from 1 to 2, which is 250 Kelvin. It's a constant. Log of V2 over V1. We get that from the table. So the work from 1 to 2 is minus 111.41 kilojoules over kilogram. That's what we found. According to the first law of thermo, we found that the heat from 1 to 2 is equal to the work from 1 to 2 because there is no change in energy. So heat from 1 to 2 is also minus 111.41. Since it's negative, this means that this is Q out. Okay, we have negative work, we have negative heat. Q out. It doesn't mean that that's all the Q out. If we found another Q that is in another process that's also negative, we have to combine it with this one. And that's also negative work because it's a contraction. The volume goes from 0.715 in volume 1 to 0.15 in volume 2, so the volume decreases. This is a contraction. Work is negative. The process from 2 to 3 is isobaric. Pressure doesn't change. This we were told. Q from 2 to 3 is equal to delta U from 2 to 3 plus work from 2 to 3. Let's calculate the work. In an isobaric process, the pressure comes out. Work is equal to pressure times the change in volume. Okay, the pressure comes out of the integral directly. Pressure is 4.75 bar, which we can convert to kilopascals by multiplying times 100. Volume 3 minus volume 2, 0.2348 minus 0.1505. Work from 2 to 3 is 40.04. It's positive work. But that's not all the positive work. We just found that the work on the previous process was minus 111. The work in this process is 40.04. According to the first law of thermal, Q is equal to W plus delta U. W is 40. Delta U from the table, U3 is equal to 278.83. U2 is 178.28. Look it up in the table. And now we find Q to be 140.69. It is positive, so that is Q into the air. It's into the system. Okay, so we already found Q out, we already found Q in, and we already found one component of the work that's negative, minus 111, one component of the work that's positive, plus 40. Let's solve the process now from 3 to 1. That's a process that's adiabatic. Q is equal to 0. So now there's no question about whether there's another component of Q in or Q out. Q out is minus 111. Q in is plus 140. There's no more Q's. Q is equal to 0, and therefore work from 3 to 1 is equal to delta U from 3 to 1. Delta U from 3 to 1 is U1 minus U3. U1 is 178.28. U3 is 278.97. This is a positive value because minus times minus is positive 100.69 kilojoules per kilogram. So we have three processes that close the cycle. In one case, we found negative work 111. In another case, we have positive work 40. And in another case, we have positive work 100. We can calculate the work net, which is the summation of all the works, minus 111 plus 40 plus 100. That yields a net amount of work of 29.32. So this power cycle involves burning fuel in order to heat in 140.69 kilojoules per every kilogram of air. That's Qn. That's in the process from 2 to 3. And it produces 29.32 kilojoules for every kilogram of air at every cycle. So the efficiency is 0.2084, or only 20.84%. That means that we're only taking advantage of 20% of the energy that we put in the form of heat and transforming it into work. It's not a very efficient cycle, but it is what it is. All right? So this is the implementation of the concepts of the second law of thermodynamics, the calculations of entropy, for the case of processes involving ideal gases, for both the constant specific heat model and the variable specific heat model. So thank you for your attention, and I'll see you next time.